Hi learners! Welcome to Math is Fun with Sir O. Today, I will be discussing Introduction to Logic. So today, we're going to know the logical connectors that we usually use in logic. So before we go to our discussion, I'm going to read first our learning outcomes. First, we're going to analyze information and the relationship between statements. Second, familiarize logical connectors. And lastly, construct the truth table to evaluate whether a given statement is a tautology or not. Would there be any questions with regard to our learning outcomes? None. So before we go to our lesson proper, I have here a short activity. So we are going to play Guess Who. So the mechanics of this game is I'm going to show you some pictures, then you're going to give your answers, meaning you're going to use your critical thinking and explain why you have chosen the person in our mystery questions. Okay, so let's start with pictures number one. Guess who? Which family are vampires? That's right. So the picture on the right side are the vampires. So they were dressed formally while they were eating on the dining table with the certain parts of human bodies, like we have your eyeballs, fingers, and of course they are drinking blood of the people. All right? Very good. So now let's proceed with our next pictures. Guess who? Which bridesmaid killed her? Is it Alice, Anna, or Ariel? That's right, it was Alice who killed the bridesmaid. The writings on the mirror give us a hint that it was Alice who killed the bride. So maybe the bride was still grasping for her breath and she managed to write the first and second letters of the name Alice. Alright? Okay. So now let's go to the next pictures. Guess who? Who killed the bride? Is it the groom or the flower girls? That's right. It was the groom who killed the bride. Why? Because the groom is hiding a gun here on the second picture. Okay? Good job. Now, let's go to the last pictures. Guess who? Who is the vampire? Is it the lady in violet dress? Is it the man sitting in the middle of the two ladies? Or is it the lady in green dress? Very good. It was the lady in green dress. Vampires are said to have no reflections when they are looking on the mirror, right? Very good and very nice. Congratulations, because you have solved our mystery using your logic. And what exactly is logic? According to Wikipedia, logic is an interdisciplinary field which studies truth and reasoning. We have two kinds of logic. The first one is informal logic, and the second one is formal logic. Informal logic seeks to characterize valid arguments informally. So meaning we are using informal logic in our day-to-day conversations with our parents or even our friends. Now, formal logic represents statements and argument patterns symbolically using formal systems such as order and logic. So whenever we speak or write, we have to follow certain rules of grammar, diction, or even pronunciation as orderly and logically possible. In other words, logic is the science of correct reasoning, meaning it is the knowledge of presenting your reasoning correctly. So now let's go to the uses of logic. So let's start with lawyers and judges. First, our lawyers and judges communicate effectively. The lawyers have good communication skills and don't have the burden of expressing themselves effectively. Next is construct valid arguments. When they present their arguments, they were backed up with substantial evidences in logical manner. Next, analyze legal contracts. They are using logic to evaluate and point out errors and illegal provisions stipulated in the contract. And lastly, make decisions. The most important part of being a judge is giving a correct judgment or verdict to the accused. He must set aside his bias to uphold the truth and justice. Next, we have our programmers. Programmers design computer software and applications. So our programmers use logic to create and innovate softwares and applications to make our lives comfortable, and the different applications that we have right now serves as entertainment and pastime of all the people. Next, let's go to electronic engineers. So they design circuits for smartphones. Due to advancement of knowledge of man, our engineers do not sleep to innovate and make designs that are user-friendly, and they create gadgets which are multifunction and high-end features. And lastly, mathematicians. Our mathematicians solve problems, find proofs to prove theorems, and establish formula to simplify solutions. Logic plays a very important role in analyzing and applying concepts of math to solve problems that usually exist in real life situations. This time, let's go to the proponents of logic. First, we have Pythagoras. He was a philosopher and mathematician. According to him, all is number and math led to the elevation of the soul. Next would be Socrates. He was also a philosopher and father of critical thinking. We have also Gottfried Wilhelm Leibniz. Combining logic and math can create symbolic language that can solve scientific problems. Next would be Augustus De Morgan. He viewed math as an abstract study of symbols. We have also George Boole. He was the father of symbolic logic, and Charles Ludwig Dodson. He is known as Lewis Carroll, and he is famous for his books, the nonsensical classics Alice's Adventures in Wonderland and Through the Looking Glass. So these stories have the game of logic and symbolic logic. So these are the pictures taken from the book The Adventures of Alice in Wonderland. On the picture, you could see that there are lots of symbolism with regard to the characters and the plot of the story. So now let's go to our everyday language. We are using a language to communicate and express our thoughts or ideas to other people. Usually, when we start a conversation, we use interrogative sentences. Like, for example, do we have a test today? This is an example of an interrogative sentence that aims to ask a question or you're asking an information from other people. Another kind of sentence would be imperative sentence. And we have here an example. Close the door. So this one is a command. So imperative sentences are used when you want somebody or if you want to request somebody to do the job for you. Another sentence would be declarative sentence. Like for example, math is a useful subject. But this declarative sentence is just an opinion. That is so because this sentence cannot be agreed by everybody. To some, math is a useful subject, but to others, math would be a difficult subject. So we have another declarative sentence. CPU is an educational institution. This kind of sentence is true because in reality, CPU is an educational institution. So this kind of sentence could be also a statement. And what is a statement? Statement is a declarative sentence that is either true or false but not both. So meaning, if you have a statement, it could be a true statement or it could be a false statement. But there is no statement which is mutually exclusive statement. Okay? Now let's have a short activity. We're going to determine whether the following is a statement or not a statement. So let's start with our statement number 1. Boracay Island is in the province of Iloilo. Is this a statement or not a statement? Very good. It is a statement. Although that our statement is false because Boracay Island is in the province of Aklan. Now let's go to our next sentence. How are you? Is this a statement or not a statement? That's right. It is not a statement because this is an interrogative sentence and it aims to ask a question. Let's go to our third sentence. 2 is a prime number. Is that a statement? Well, it is indeed a statement. Right? Very easy. Now let's go to our fourth sentence. X plus 1 is equal to 5 when x is equal to 5. Is this a statement or not a statement? Very good. Although our mathematical sentence is false because the value of x is not equal to 5 when x plus 1 is equal to 5. It should have been 4, right? Any questions so far? None. Now let's go to simple and compound statements. Simple statement is a statement that conveys a single idea. Meaning, if you have a statement that has only one idea, it is a simple statement. Example, 2 is an even number. So our statement has only one idea. What is 2? So it is an even number. Another statement, 2 is a prime number. So this is also a simple statement because 2 is regarded as a prime number. So it has only one or single idea. All right? Now let's go to compound statement. Compound statement is a statement that expresses two or more ideas. So if you have two or more ideas embedded in one statement, that would be a compound statement. Example, 2 is an even and prime number. So our 2 is regarded with two different ideas. So we have there, it is an even and at the same time, a prime number. Another example, I like to eat fruits and vegetables. So there were two ideas that is also embedded in our statement. So the two different ideas that we have there are fruits and vegetables. Okay? Any questions so far? None. All right? So now let's go to truth value and truth tables. The truth value of a simple statement is either true or false. So meaning you only have two truth values if you have a simple statement. It would be only true or false. Okay? How about if you have a compound statement? So the truth value of a compound statement depends on the truth values of its simple statements and its connectives. So meaning you have to examine first the truth values of the two simple statements and the connectives that you have used. How about our truth table? The truth table is a table that shows the truth value of a compound statement for all possible truth values of its simple statements. Meaning we are using only truth value for compound statements. So in order for us to know the truth value of our statement, then we have to examine all the possible truth values of the simple statements in our one big statement. or one long statement. For you to be able to understand the truth value and truth table, we're going to have an example. Since the proposition has two possible truth values, for only one proposition, we have two truth values. So that would be true or false. To determine the number of rows where n is the number of propositions, then we're going to use the formula 2 raised to n. So it is the same in getting the subsets if we have given a number of elements of our set. So we have here two possible truth values for one proposition, because if we're going to substitute the value of 1 in our formula, that would be 2 raised to n, and our n is equal to 1, and that would be equal to 2 raised to 1. And 2 raised to 1 is equal to 2, right? So that's why we have only your true and false truth values. So how about if we have two propositions? So this time, we have propositions P and Q. How are we going to construct the truth table? Of course, you're going to use the formula. So basically, that would be 2 raised to n. And our n there is equal to 2, right? So 2 raised to 2 is equal to 4, right? Because 2 times 2 is equal to 4. So the 4 that we have here would be the number of rows for our propositions P and Q. So to construct our table, we will have two columns, one column for P and one column for Q. And at the same time, we will have 4 rows. So it would look like this. So we have here the column P and we have here column Q, right? And each of the columns that we have for our proposition, so we have there 4 rows, okay? So for proposition P, we have 2 true and 2 false, right? So they are written like this. For our proposition Q, we have also 2 true and 2 false. They are written like this. So they are written alternately, all right? Now, how about if we have 3 propositions? So this time we have P, Q, and R propositions. So using the formula, that would be 2 raised to n, and it is equal to 2 raised to 3, or 2 cubed, that is equal to 8. So meaning for propositions P, Q, and R, we will have a total of 8 rows. So this would be the table for our propositions P, Q, and R. For our column P, so we have here 4 true and 4 false, okay? And they are written like this, okay? And for our proposition Q, we have also 4 true, 4 false. So they are written like this. So 2 true, followed by 2 false, and followed by 2 true and 2 false. And lastly, we have your proposition R. So we have also 4 true and 4 false, but they are written alternately. Okay? Any questions so far in constructing our truth table? None? All right. So now let's go to logical connectors. So the first one will be our negation. The negation of a proposition P is denoted by this symbol. So this is read as not P and is defined through the truth table. So here in our truth table, let's regard our proposition Q as our negation. So meaning Q there is equal to not P. So if our proposition P is true, then our not P is false. And if our proposition P is false, then our not P is true. Right? So we have here some examples. Write the negation of the statement. So we have there P1, P2, and P3. So P1, 2 is an odd number. So when you are going to use negation, usually you're going to get the opposite idea of your statement. So you can say 2 is an even number. So instead of saying odd number, then it would be replaced with an even number. But you have to also to indicate your symbol. This is not P1, right? So that would be 2 is an even number. The next one, P sub 2, the dog does not need to be fed. We're going to check our sentence. It is a negative sentence because we have here our word not. Okay? So meaning we're going to get the opposite of our statement. And that would be not P sub 2, the dog needs to be fed. So look at this. We just remove our words does not to make it a positive statement. But of course, if you're going to do that, you have also to observe your grammatical rules. Okay? So if your subject is singular, then your verb should be in S form, right? But if your subject is plural, then your verb should be in simple form, meaning there will be no S. So if you're using words do, does, and did, so you don't need to use your verbs to be in their S form. It should be only written in simple form. All right? Any question? Okay. So now let's go to our P sub 3. The tinikling is the most difficult dance. So if you're going to understand our statement, it is like a negative statement because of the word difficult. So we're going to negate this statement, and that would be not P sub 3. The tinikling is not the most difficult dance. So by the way, our example number 3 will be the safest of all. All you need to do is just put the word not to negate your statement. So where do you usually put the word not? So our linking verbs like is usually precedes with the word not. So you have to watch out your linking verbs. For our singular subject, for present, it would be is, and for our past tense, it would be was. Now, if you have your plural subjects, for the present tense, it would be are, and for the past tense, it would be were. Okay? Any questions so far with our negation? None. All right. Now let's go to the next connector. So this time it is the conjunction. So the conjunction of a proposition P is denoted by this symbol. So this is read as P and Q. Okay. So please remember that if we have this symbol, it means that we're going to use our conjunction, which is your and. Okay. And that is defined through the truth table. So for example, if your proposition P is true and your proposition Q is true, then our P and Q is also true. So same true with our propositions P and Q, which are both false. Then our P and Q is also false. Now here in the middle, so either of our propositions P and Q has a false truth value, then it follows that our P and Q are also false. Okay? Any question? All right. So now let's have some examples. So let P and Q be the following propositions. For our proposition P, today is Friday. Our proposition Q, it is raining. So let's say that today is Wednesday. It is not a Friday, right? So our proposition P is false. Now let's check our situation. Is it raining right now? It is not raining right now. So meaning this is also a false proposition. So therefore, if we're going to use our truth table for our proposition P, which is false, and our proposition Q, which is also false, then it follows that our P and Q is also false. So this time, we're going to write our propositions P and Q using the symbols. Write the following conjunction as English sentences. So the first one is our P and Q. So meaning we're going to combine the two single statements in one statement, right? But then we're going to use our connector or our connective, which is your and. So P and Q is written as, right? So our proposition P, today is Friday, and our proposition Q, it is raining. But then they are connected with our conjunction or connective, which is your and. Okay? So this is how you write your symbol using your English sentence. Okay? How about this one for our letter B? So we have our proposition P, then followed by our and, then we have to negate our proposition Q. So if we're going to negate your proposition Q, it is raining. So this time we're going to insert there the word not after your linking verb is. So it will become it is not raining. So if we're going to write this using our English sentence, it would be today is Friday, our proposition P, followed by our and, then our negation Q, which is it is not raining. All right? Any question with our conjunction? None. So now let's go to the next one. This time we have the disjunction. The disjunction of a proposition P and Q is denoted by P, V, Q. So our V here is like an inverted symbol of our conjunction. So that is read as P or Q. Okay? And it is defined through our truth table. So for example, our propositions P and Q are both true. It follows that our P or Q is also true. But if our propositions P and Q are both false, it follows that our P or Q is also false. Now, in the middle, if either of our propositions P and Q has a true truth value, then our P or Q there should always be true. The truth table tells us that the disjunction P or Q is false only when both disjunct P and Q are false. Right? So we have here, if both P and Q are false, then it is always false. Right? So now let's have some examples. So let P, Q, and R be the following propositions. For proposition P, Enrique has a date with Liza. Proposition Q, James is sleeping. And proposition R, Daniel is eating. Express the following propositions in English sentences or in symbols as the case may be. So for letter A, we have your P or Q. So meaning we're going to use only two propositions here, P and Q only. So it follows that your proposition P, Enrique has a date with Liza, followed by this symbol, which is your connector or, okay? And then you're going to write your proposition Q, James is sleeping. So it is Enrique has a date with Liza, or James is sleeping. So now let's go to letter B, Q or negation R. So this time we're going to use the propositions Q and R, but our R should be negated. So we're going to insert the word not right after our linking verb is. Okay? So it will be written as James is sleeping, followed by or, then Daniel is not eating. Alright? Any question? How about our letter C? So P or, then we have here another propositions which are grouped. So we have your Q and R which are grouped inside our parentheses. How are we going to write that in our English sentence? So first, you consider your proposition P. Enrique has a date with Liza. If we're going to check, we have propositions Q and R are grouped as one proposition. So it follows that our first proposition, P, has a comma, right? To indicate that this proposition is not included in our group of two propositions here, okay? Then, of course, we have your or, then followed by our propositions inside your parentheses. James is sleeping or Daniel is eating. Right? So again, you're going to place a comma here to indicate that this is the first proposition and it's not included in the two propositions Q and R. Right? Now let's go to our letter D. This time we have our English statement. And we are going to convert this using our symbols. So we have here, either Enrique has a date with Liza, or James is sleeping, or Daniel is eating. What do you think will our symbol look like? All right. So we have here, Enrique has a date with Liza, or James is sleeping, followed by this comma. So meaning the two propositions that we have here, P and Q, should be placed inside our parentheses, followed by our connective or, then proceed with your last proposition R, which is Daniel is eating. So our symbol would look like this, right? So parentheses, P or Q, then we have your or R, right? Any questions so far? None. So now let's go to our letter E. So either Enrique has a date with Liza, then we have here our comma, right? Or James is sleeping and Daniel is eating. So this time, this will be the first part that we're going to write. So this time, James is sleeping and Daniel is eating will be placed inside our parentheses. But also, you have to be careful that our connective used here is and. Okay? So you have also to use your connective correctly. So it follows that our symbol would look like this. So proposition P, either Enrique has a date with Liza, then followed by our connective or. So this is our connective or. Then we have to place our propositions Q and R inside the parentheses, but then we have to use our connective and. So that would be open parentheses Q and R followed by close parentheses. Okay, so any questions so far? None. All right. So now let's go to our fourth logical connector. So this time it is named as our conditional. The conditional of a propositions P and Q is denoted by this symbol that is read as if P, then Q. And it is defined through our truth table. So for our propositions P and Q, if they are both true, then it follows that our if P then Q is also true, right? Now in the middle, right? So look at this. So whatever is the truth value of your Q, so you're going to follow the truth value in your if P then Q. So if our Q is F, then our if P then Q is also an F, right? If our Q is T or true, then our if P then Q is also T or true. Okay? Any question? The conditional if P then Q may also be read as P implies Q. So the proposition P is called the hypothesis, while the proposition Q is called the proposition. Okay. So as I said that our proposition Q, right, is called the proposition. So whatever is the truth value of our Q here in the middle, that would be the truth value that you're going to use in your if P then Q, right? So let's have an example for this. Suppose that Kyle is a grade 12 student. Consider the following conditionals. So for our P sub 1, if Kyle is in grade 12, then he is a senior high school student. So we're going to analyze the truth value of our P sub 1. So let's say if Kyle is in grade 12, this is a true statement. Then the second statement says he is a senior high school student. And that is also true, right? Because if you are a senior high school student, you are in grade 12. Okay? So both are true. Then it follows that our if P, then Q is also true. As what we have here in our P sub 1 in our solution. So it is true because the first row of the truth table asserts, right? How about our P sub 2? If Kyle is in grade 12, then he is working as an engineer. So the first statement there is, or our proposition P there is true, but then our proposition Q is not true. That would be false. So true, then followed by false. Then our if P, then Q is also false. So our P sub 2 is false since our second row, it should be second row, not first row, okay? of the truth table indicates false, right? Now, how about our last statement? If Kyle has a degree in tourism, then he believes in true love. So look at our solution. It is true regardless of the truth value of its conclusion as shown in the last two rows of the truth table. So meaning, if your proposition Q there says it's true, no, even you have false in your proposition P, then our if P then Q is always true. Okay? And if both of your propositions P and Q are false, then you will have your if P then Q, which is a true statement. Right? Any questions so far? None. Okay. So now let's go to the last logical connector, and it is biconditional. The biconditional of a proposition P and Q is denoted by this symbol. So we have your two arrowheads pointing to your P and Q. So that is read as if P and only if Q, and is defined through our truth table. Okay. If both of them, the propositions P and Q, are false, then our if P and only if Q, that is also true, right? But look at this. So in the middle, so whenever you have either your proposition P or Q is false, then your if P and only if Q is always false, right? So the biconditional may also be written as if P IFFQ, right? So the proposition P and Q are the components of the biconditional. So let's have our examples for this. Okay, using the same example in our conditional. So if Kyle is in grade 12, then he is a senior high school student. So both of our statements there, P and Q propositions, are true. Then our if P and only if Q is also true, right? Then for our next statement, P sub 2, if Kyle is in grade 12, then he's working as an engineer, right? So if the first proposition is true, the second proposition is false, then the answer would be a false, right? Because according to our table, that if P and if and only Q, then that is false, right? Now for our third statement, if Kyle has a degree in tourism, then he believes in true love, right? So it follows that if our proposition P here is true, then our proposition Q is false, right? So it would be a false. So our if P and if only Q, then that would be false. How about if we say that Kyle is not a tourism student? He is a grade 12 student. So that will become false, right? Then we assume that he believes in true love, and that would be our proposition Q, which is a true. So even though that our proposition Q is true, then it follows that our if P and if only Q, then that is a false, right? Okay. So how about if Kyle has a degree in tourism is a false statement, and then he believes in true love is also a false statement, then eventually we will have a true truth value. All right. So any questions so far? Okay. So for you to familiarize our truth table, so I have here the summary of our truth table for each of our connectors, right? So we have our proposition P, proposition Q, we have your P or Q, P and Q. If P then Q, you have also if P and if only Q, and you have your negation P. So just familiarize your truth values using this table. Okay? So we have also our summary of logical connectors. So please also familiarize our connective, our symbol, our compound statement, their symbolic form, and the type of compound statement. Right? Okay, so this will serve as your assignment for this lesson. So in every item, indicate what statements P, Q, or R might stand for the given compound statement. Any questions so far? So thank you so much for listening and watching this video. That would be all for today. So of course, I would always encourage you to please like and share this video to your friends and classmates. And please consider subscribing to this YouTube channel because I will be very glad and grateful to make more video lessons for you to make your math learning journey a wholesome and fun. So this time, I'm going to bid goodbye and always keep safe and God bless everyone. This is your Sir O saying laban lang.